So when we started the class a week ago, I think it was, yeah, a week ago, we were able to classify matter as a pure substance or a mixture. And if it was a pure substance, we classify that substance as an element or a compound. And when we talk about elements, we said that elements are made of atoms and that elements are the smallest I can divide matter. So elements are made of these small particles called atoms, and atoms have some particles in them. But I will not be doing justice to the topic unless I talk about how those particles in the atom were discovered. So what we are going to do first is go through the history of the atom, and I'm going to point out a few things, and some are more important than others, and I'm going to let you know, okay, from these scientists, this is what you need to know. From these scientists, this is what you need to know, so you don't have to memorize or remember every single thing that I'm going to show you. Now, so we go through some laws, some evidence that's going to allow us to describe the structure of the atom. And there's going to be some math involved because we're going to have to calculate particles, we're going to have to calculate atomic mass, and so on. And some of these you already know how to do from intro to chem, but now we're going to opt it up in the information that I'm going to provide to you. Now, before we do and jump into the scientists, there's three laws that you have to remember. The law of conservation of mass, the law of definite composition, the law of multiple proportions. The law of conservation of mass says that the mass that you start with, you have to justify at the end, because mass is not created or destroyed, only transformed. So if in a chemical reaction you start with, let's say, 100 grams of reactants, at the end you need to have 100 grams of products. You cannot have more products, you cannot have less products, and if that happens, you have to be able to explain where that mass difference is going or coming from. So that's the law of conservation of mass. I don't really care that Lavoisier in 1789 said that. All I care is that you understand that law of conservation of mass. Then we have the law of definite composition. We said that if you have different compounds made of the same element, as long as the ratio between the two elements is the same, then they are the same compound. So if jar A, jar B, and jar C are made of carbon and hydrogen, and the ratio is 5.33 grams to 1 gram of hydrogen, then all three are isooctane. If one of them, the mass of carbon or the mass of hydrogen, is different, then it's no longer isooctane, it is something else. For it to be the same compound in different locations, it needs to have the same ratio between the elements. So the ratio between carbon and hydrogen has to be the same. And then lastly, the law of multiple proportions. Sometimes you can have the same elements combining together. That doesn't mean they're the same or not. You have to look at them, but when they combine, they're going to combine as a small whole number ratio, meaning if I had something like C4 H10, when those two elements combine, I had to be able to combine it at the lowest atom number ratio. So because the 4 and the 10 I can simplify to a 2 and a 5, that means that the C2H5 is the smallest ratio that I can combine those two elements. And that's what the law of multiple proportions says. We are going to use this law of multiple proportions when we start talking about the mole and calculate empirical formulas and molecular formulas. That's where this law applies. The law of definite composition applies all the time because you can compare two things. I'm going to tell you right now, you're going to have a problem based on that in the exam, on that law, and on the first two laws, because they're pretty straightforward to deal with. The other one we'll deal with when we get to the mole. Okay, so before we jump to Dalton, because Dalton was not the first scientist that talked about the atom, I like to talk about one that is usually forgotten, and that is Democritus. And that's why it's his. Okay, I don't know if that's Dalton or Democritus. We're not going to assume. Democritus was a Greek scientist way, way, way back to the Greek times. He took a piece of bread and he said, if I take this piece of bread and start cutting it in pieces, there's going to be a time where I cannot cut that piece of bread anymore. So that smallest piece of bread that I cut, I'm going to call it indivisible, and I'm going to call it atomos. So Democritus came up with the word atomos, which means indivisible, which is the word that is used to call the atom. The problem with Democritus was that he went to the Greek council. I have this thing that I call atomos. And they all laugh. Because where is it? I don't see it. They couldn't see it because it's so small. But he knew that it has to be there. Now, one of the people in the Greek council was Aristotle, which was one of Democritus' disciples. And he said, that sounds like it's kind of correct. I'm going to modify it. So he did modify it, presented it as a new idea, and that is great. And they believe him. So Democritus didn't get the credit for discovering the atom. Aristotle did. So we don't talk about Aristotle, we talk about Democritus. And that was back in the time for the Greeks. Now, I want you to get this in your head. Back then, there were not instruments or anything that could show you the atom, but all these scientists were able to come out with this idea that are still valid today. Think about that and how great that is, because someone in here is going to go to the industry once you graduate from college, and you're going to make a discovery that not everybody is going to accept at the moment because they don't have enough information or the instrumentation to validate that. But later on, they will. So that's what happens later on, much later on. Dalton, he was an English guy. He started looking at the atom idea, and he said, yeah, I agree with that. I still believe there's an atom that is indivisible, but I'm going to say it is very tiny and indestructible. And instead of calling it atomos, I'm just going to call it atom. And that's what he did. And he said, matter is made of these tiny indestructible particles called atoms. He said they look like a sphere. And we said that his model is like the Wheeler model, because it's just like a small hard sphere ball. He also said, if I have an element of carbon and I pick another element of carbon, they will have the same identical properties because they're the same element. So if an element is made of particles that are of the same type of atom, they have the same properties. And then he piggybacked that definition and said, if I can combine two different atoms with different properties, I'm going to get a new type of material that has new properties that are called compounds. So he was able to define what an element is and what a compound is. The only thing that he did wrong, and that is the last statement, is to say that atoms are not destroyed during chemical changes, they're simply rearranged. That is no longer valid. That doesn't hold up anymore because we know through nuclear reactions that I can create and destroy atoms. But based on the limited instrumentation and knowledge he had, he was able to come up with a theory that is 90% valid to this day. Okay. Hold on a second. See what time. Oh, we have plenty of time. Okay. So now we're going to go over two experiments. Actually, three. One of those I don't go too much in detail, but two experiments. You need to know the next two experiments very well in terms of this scientist used this instrument and discovered this. That's the main thing you need to know. So we have this scientist called JJ something. I can never say his name right. So we all call it JJ. Use this thing called a cathode ray tube. Okay. A cathode ray tube is, I don't know if, well, you guys are too young, but maybe if you go to your grandparents' house, you remember those huge TVs that were very big, that had a huge screen, a big background that has a big tube inside. That's a cathode ray tube. So he used that because he had a way to have an electrode on one end and a detector on the other end. What he did was he put a voltage to that electrode, and particles went from that side to the other side. Now, this screen that he had in here is a positive detector. So if the particles go from one side to the other and it gets attracted to that positive side, what does it say about the identity of that particle? Is it positive or negative? If I get attracted by a positive side, I have to be negative, because if I was positive, I will repel each other. So similar charges repel each other, different charges attract each other. So he found out that that particle coming out of the filament of this cathode in here is negative in nature. So he said, okay, I have a negative particle that I can control. And I have some slides coming after this one, and I'll show you that. But the main idea here is that I'm going to call that particle electron. So he discovered that the first particle of the atom is the electron. And that particle is very, very, very small. But it has a charge of minus 1.76 times 10 to the 8th coulombs per gram. I don't do much with the charge to mass ratio, but to say that that mass charge to mass ratio is very, very, very small compared to the other two particles that we'll see in the atom. So JJ discovered the electron using the cathode ray tube. Now, Dalton said that the atom looked like a sphere that was indestructible and hard. JJ said, okay, I'm going to say that it's like a plum cake because in England, the plum cakes are made of bread and raisins embedded. So he said, okay, the raisins are like the electrons, and then the dough is like the rest of the atom. So he said that the atom has embedded negative particles inside the atom. We know now that that's not correct, but that's what he said. Moving on. Okay, I don't have those in here, but so I won't go over them. You see these two plates in here? These are magnets that have a positive and negative side. When the particle comes through, it gets attracted towards the positive side. So that's another reason why you know that a particle is negative. So you can add a magnet and control the direction of that electron. And when you look at your outline in your on Canvas, you'll see that there's a few slides that have those pictures and explain that a little bit better. That's just there for your knowledge. I am not going to ask you about those descriptions in here. So for JJ, the electron using the cathode ray tube, and the model was a plum model. Plum putty model, just to be more accurate. All righty. How are we doing here? Okay, hanging in there. Awesome. Another experiment, and this one is one of those experiments that doesn't get covered much in chemistry, and that is Millikan's oil drop experiment. This experiment is just here to show that I can calculate the mass of the electron doing an experiment where I can take oil particles and I measure how they behave going through an electric field. It's more complicated than just this oversimplification. So if I need to ask you about the oil drop experiment, just know that it was used to determine the mass of the electron, which was 9.11 times 10 to the minus 28. That's a very, very small mass. So for all practical purposes, we say the electron has no mass. Compared to the other two particles that have not been discovered yet, and you know, but the scientists didn't. Now the experiment, and this is the experiment that you do have to remember everything about. It's called the gold foil experiment. I'm pretty sure you remember that one. In this experiment, Rutherford which he was a German, took a radioactive emitter that emitted alpha ray particles. Those alpha ray particles are positive in nature. And then he used that to bombard a gold foil that he placed in the middle, surrounded by a detector made out of zinc sulfide. He used that zinc sulfide screen detector to be able to see what happens to those alpha ray particles as they went through the gold foil. His expectation was, okay, if I'm going to bombard the gold foil with particles, they're all going to go through, no problem, because it's like hitting a piece of paper with a gun. It's going to go through. But that's not what he saw. He saw that three things happen. And those are the three things you need to remember. So yes, some of them passed through. That told him, okay, the atom is made of empty space. Then he saw that some particles bounce back. So that's two. And they bounce back because, okay, if I'm hitting the wall with a gun and the bullet comes back, there must be there's something in that wall that's stopping that bullet to going through. So he said, okay, I know there's something there. It's probably a nucleus. It's probably something in there that I'm going to call a nucleus. So he said that the atom has a nucleus. And then he saw a third thing, and that was that sometimes when that alpha particle came close to the nucleus, it got deflected. So I have a particle that's getting deflected. So that nucleus must have a charge. So if the alpha particle is positive, that nucleus has to be positive as well. Because that's the only way that that particle can be deflected. If it was negative, it will be attracted towards the nucleus, and that's not what happens. Oh my gosh. So Rutherford and gold foil So he discovered a proton, which is a positive particle, and he said the atom is mostly empty space with a dense positive nucleus. And that's what you need to remember. Besides, if I give you a diagram of the experiment, you need to be able to describe the three things that happen and why they happen. So it goes through because the atom is almost empty space. It bounced back because there's a dense nucleus. It got deflected because the nucleus is positive. Boom, you are good. So now he took the model from JJ, that was a plum pudding, and he said, okay, the atom has a small nucleus that's positive, which all those negative particles, they must be outside. So now we have an atom that has protons and have electrons. We usually don't talk about neutrons, but the atom is also made of neutrons. The neutrons are there to stabilize the atom. So the neutrons are in the nucleus to stabilize the atom. And that's all I'm going to say about neutrons. Oh, the other, well, yeah. So just to finalize this scientist thing, we have Thomson and Rutherford. Thomson was a plum pudding, Rutherford was a nuclear atom. Thomson, they said that the mass of the atom is spread out throughout the whole thing, while Rutherford says it's in the center. The positive charge in Thomson says that it is there all throughout, but Rutherford says no, 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 it's in the nucleus. And then the alpha path for Thomson, he really didn't say anything, even though he says here straight through, but that particles could go through that plum pudding. But Rutherford said that there could be some deflection in there because that nucleus can be positive and the particles are positive, so there can be some occasional deflection. So being able to compare both experiments is a good thing. So please don't forget that slide. Now, taking all the information now that we have, we see that the atom is made of three particles. It's made of protons, neutrons, and electrons. Protons I'm going to describe as a P plus, neutrons as an N0, and electrons as an E minus. And this is where I start making jokes that make no sense or are not funny at all. So why is it that the nucleus doesn't pay going to the bar? Because it's not charged. Just wait until I get to the periodic table. I had like 9 puns. Some of them are funny, some of them are not. You don't have to laugh. You don't have to entertain me. Just to make the class a little more vivid. Okay, the mass of the proton and the neutron is very close to each other, so we say it's around 1 AMU. And the electron we say is almost no mass. So what you're gonna say is around 0 AMUs, just to say that the mass of the atom is in the nucleus, not outside. Then, comparing the sizes of those particles, the protons and neutrons are somewhat bigger than the electron. And that's why that mass is in that the nucleus. Okay, let me see. We'll do a couple slides more and then we stop. Let me see. Okay. Yeah, we'll do a couple ones. So atoms. You have protons, you have neutrons, you have electrons. They're not all equal. But there's 3 things that can happen. If I look at the protons first, I can change the protons of the element. If I do that, I change the element. Because protons tells you the atomic number of the element. It tells you the position in the periodic table. So the atomic number, which are the small numbers in each one of those squares in the periodic table, tells you how many protons that atom has. If you change the number of protons, you change the atomic number, which changes the element. So the protons gives you the identity of the atom. It tells you what you're dealing with. I can change the neutrons, and that is only going to change the mass. Or I can change the electrons, and then that will change the charge. We are going to deal with those 2 cases next week. We're not going to do it today. So the important one here is the protons do not touch protons at all, because that changes the atom. The other thing that we are going to say in here, and I'm going to do it in a new slide just to make sure you don't forget is atoms are neutral, meaning they don't have a charge. So if an atom is neutral, what are the two particles that could have a charge? The protons and the electrons. So what does that say? If I don't have any charge, those two have to be equal. So for everything you do from now on, the atom is neutral unless I tell you otherwise or I give you information that tells you otherwise. That simplifies calculating particles quite a bit. Okay, let me see. Okay, so do I have? No, I don't have it. Okay, so let me do this. Let's say I look at a piece of the periodic table. That piece has a letter. That's just the symbol. Of the element. Then, because of the protons, we have the atomic number. The atomic number is a small number. It's usually the bottom corner on the left or the top right corner. Is a single number that changes from element to element. Then we have a number with decimals. That is the atomic mass. And that's the basic minimal information any periodic table will have. Now, some periodic tables have more information because some of them, some charges, those are called oxidation states. We'll deal with those when we get to redox reactions, when we do type of reactions. There's a different way we are going to deal with charges when we start talking about how to name compounds. We'll do that next week. Sometimes you have a number at the bottom that looks like, let's see, 2. Let's say it's 2H. That is the electronic configuration. We are going to deal with electronic configuration and completely different than some periodic tables do. We don't do electronic configurations until a couple of weeks before the end of the summer. There's more information that you could have. You can have a state of matter. So it tells you if it's solid, liquid, or gas. So you need to know which ones are gases. You need to know which ones are liquids, which ones are gases. We're going to look at that when we do the basics of the periodic table next week. So that's the basic type of information. So now that we know how to decode reading the periodic table is when we can move and look at this lighting here. Because now I can use the symbol and write the atomic number at the bottom and the mass number on top on the left side. And that is called a standard notation or isotopic notation. It tells you the mass of that element, the atomic mass of that element, and the atomic number. Now, in all reality, I don't have to write the Z value in there because if I know the symbol, I know what element I'm talking about. So it's a little bit redundant, but that's the notation they came up with. The only thing you have to remember is that the chemical symbol, if it is one letter, is uppercase. If it is two letters, it's uppercase, lowercase. I have it in here, so I just might as well. The mass number is the number of protons plus the number of neutrons, and the atomic number is just the number of protons. So that's one way you can get that information. The other way is by writing the name of the element followed by the mass number. And I say atomic mass in there, it should be a mass number. I'm sorry. I'm glad I caught that. Mass number is the rounded atomic mass. And I'm going to pause in here and ask you, why do I have to round the atomic mass to get a mass number? Why am I rounding? Think about what we're dealing here. We're dealing with particles, right? If I don't round, I have a number with a decimal. If I have a number with a decimal, it implies that I have a fraction of something. Can I have a fraction of a proton? Can I have a fraction of an electron? No, I can't. I either have an electron or I have a proton. So by rounding the atomic mass to a mass number, I'm making sure that I'm dealing with whole numbers that represent whole particles. So two different ways of representing the same information. So neon 20 tells you that it has a mass number of 20, but when I look at neon, the mass of neon is not 20 because the mass of neon is 20.180. So we're going to have to reconcile that situation. The other situation is that sometimes that symbol could have a plus or a minus. So we're going to have to deal with that as well. And that's what we'll do next class because I'm going to stop here. Yep. So I'm going to let you go. So I'm just going to pick up, go to my office really quick, drop everything, and I'll meet you in the lab in a couple minutes. For the lab, all we're doing is collecting data because the rest you can do at home. So it will not be a super long lab either. Okay, so I'll see you in a little bit. Mm-hmm.
Oh, we could just go to the store. No. So it's coming today. Is it okay if I just use it on Monday?
Yeah, for today is fine.
Okay.
Yes, sir.